what I'd like to do now is to give a lecture on apportionment. This is very similar to what we did with the voting section, because I'm going to give you 4 different methods to allocate these votes, these seats, and you just need to know which is which and how to apply them. So I'll start off with this problem down here. It's a mini problem. I don't have 50 rows for 50 states, but it's a similar thing. This is the Republic of Amador. It's composed of 5 states instead of 50, A, B, C, D. So here are the states, A, B, C, D, and E. And according to the country's constitution, the Congress will have 200 seats. So in our Congress or our electoral college, we have 538. In this particular republic, they have 200 seats. So all they have to do is to award those 200 seats to these 5 states. Why not just take 200 and divide by 5? One way to do it, if you have 200 seats and you have 5 states, well, why not just take 200 divided by 5 and give 40 and call it good? Every state gets 40 votes, 40 seats, and that's it. Well, we're done. Well, we're done, except state E is not very happy with that because they have a huge population. And so if they're only going to get 40 seats like everybody else, these other states that have smaller populations, you know, just like the problem that I mentioned earlier, you know, their votes are more powerful than in state E. So we're going to allocate those 200 seats, not just equally, but equitably, where we're going to award seats based on the population. All of these are about the same. These 2 should get about the same number of seats because they have about the same population. These 2 are kind of the same, but this one is about 3 to 4 times larger than this one. So maybe they should get 3 to 4 times the number of electoral college votes, or seats in this case. So here are the methods to split those votes down. We're not going to do it this way. This is not one of our methods. The first thing that you'll notice is that the methods are named after some names that are maybe names that you're familiar with. Hamilton, yep, that's the same guy. Alexander Hamilton. On the $10 bill, the guy the play was named after, that guy. He did mathematics. And back then, it was a big problem for the US to actually decide how they're going to allocate votes. This is Thomas Jefferson. He came up with a new method, and his method was different than Hamilton's. Adams was like Jefferson's, again, John Adams, same guy. And Webster was another guy around at the time, though he's not as famous. I think he was a signer of the Declaration of Independence, however. So they came up with 4 different methods. And these 4 methods are not used today. The ones that we use today are similarly done, but it's called the Huntington Hill method. So I'd like to go through the methods and show you how we allocate these seats. The first one is Hamilton's method. We're going to calculate the standard quota. So we have the standard divisor, and this is going to be called or labeled D for the standard divisor. And the D is equal to the total population divided by the number of seats. And this calculation you're going to do no matter what method you use. But you first determine the standard divisor. And so in our first example, this particular republic has 10,000 people, and there are 200 seats. So the total population is 10,000, and the number of seats is 200. And when you do the division, you get 50. So 50 is what we call the standard divisor. All right, so this is kind of before we get into the method you want to calculate this. Hamilton's method says calculate each state's standard quota. So the standard quota is equal to the state population divided by that standard divisor. I'll just write it that way, divided by D. So I'll put a little formula on the top of that column. It's population. Now this is population of the state now, divided by the standard divisor. So in this cell right here, you're going to put the population divided by 50, and that's going to give you the number you put here. And you'll do that for each one of the states. Now, what should happen when you do that is when you sum all these together, the sum should equal the number of seats, 200. That's why we use it. So I'm going to just go ahead and type these in. Now, then I'm going to show you a quicker way to get all of these calculations without doing all this typing on your home screen. Running out of space. So 22.24. And you need to write the entire decimal, at least 3 decimal places. And even in cases where we don't have 2 decimal places, these have 2 decimal places, so I'm adding another one onto that. And the last one is 98.7. So I'll write 70. Now you can check, but if you add those 5 numbers together, you're going to get 200 right on the nose. Right on the nose. Now, but we want these folks here to serve on a committee or on in a Senate or in this case a Congress. So we can't award a fraction of a person. And this whole problem is to decide who gets the fraction. And it's all based on the upper and lower quota. So here's how you do these two. So these 3 columns are going to be done automatically in these problems. And then you start the 1, 2, 3, 4 methods after that. But the initial steps will be determine what the standard divisor is, divide each state's population by that standard divisor, and then write the lower quota and then the upper quota. And so this is very easy to do. The lower quota, or just imagine putting that number 22.24 between 2 whole numbers. The lesser whole number is 22, and the upper whole number is 23. So 22.22 is between 22 and 23. So 22 is the lower quota and 23 is the upper quota. Another way to think about it is just to get the lower quota, just get rid of all the decimal points and write the whole number piece, 22, 26, 30, and 98. Notice we're not rounding, we're just truncating off the decimal piece. Then what we're going to do to get the upper quota, we're going to add 1 to the lower quota. So if you want to go from here to here, just add 1. There's always going to be a jump of 1. 22 to 23, 26 to 27, 30 to 31, and 98 to 99. Now, when we get rid of the fractions, these columns here do not any longer add up to 200. Rather, this column adds up to 198, and since we're adding 5, this column is going to add up to 203. Now, we only have 200 seats, so we can't give everybody this number because it's going to be larger than 200. We're going to get 203 seats. We would need 203 seats. And if we just assign every state this whole number of senators, then we're going to have 2 votes left over. And so all 4 of these methods answer the question, what are we going to do with those last 2 votes? Who gets them? Which state gets those last 2 votes? All right, and so I'm going to show you the methods. Hamilton's method is this. To go from 198 to 200, we need to give away 2 more votes above the lower quota. So who do we give the votes to? Well, here's what Hamilton's method says. All of these decimals here are somewhere between 0 and 1. You've got the smaller decimal points like 0.01 and 0.25, and you've got the bigger decimals like 0.99 and 0.98 and in there. So what you do is you go look at the decimal part of each one of these numbers in the standard quota and identify the 2, since we're giving away 2 votes, the 2 largest decimal fractions to the right of the decimal point. So which 2 states have the highest decimal to the right of the decimal point? Hamilton's method, the way that it's going to assign those last 2 votes to bring us up to 200 seats is it's going to award 1 vote to 2 different states based on the highest decimal piece that they have. They're the closest to the next whole number. That we have E, because that's 0.70, and 0.40. Those are the 2 highest compared to all these other numbers. So we're going to bump state C up to its upper quota, and we're going to bump state E up to its upper quota, but all of the other states remain with their lower quota. So 22, 22, and 30. And when you add all those up, you get to 200, and so you're good. So this is Hamilton's method, just by inspection, looking at the decimal pieces of what remains in the standard quota. Now, it could be the case that these other methods give you the same 5 numbers. That'd be great if it did. Any method we choose gives us the same number of seats to make up the Congress. It's usually not the case, however. In summary, Hamilton's method. Calculate the standard quota. That's going to be the first step for all of these. Round each state's standard quota down to the nearest whole number. Rounded these down. Round up if you want the upper quota. And then we're going to award one more vote based on the largest decimal. That's what this is saying right here. Give an extra vote, one at a time, to the state with the largest decimal part in their standard quota, until all of the electoral votes are allocated. So every time you get to this point, you have to decide how many additional votes need to be allocated. If we added these 5 numbers and got 195, then we would have to allocate 5. Now, it wouldn't be 5 in this case because that would just mean we would give 1 to everybody, and that's not going to happen. Okay, let's look at the next method. So that's method 1, and that's Hamilton's method. The next one is Jefferson's method. For Jefferson's method, notice that the D, they reduced it. It used to be 50, the standard divisor. But in Jefferson's method, we're going to lower that standard divisor a little bit and then divide all of the populations by that standard or that modified divisor there. And you're going to get a bunch of different numbers here. And then what you do with those different numbers is to round down, which means basically truncate the decimal piece. Okay, you probably don't want your calculator to look like this. It's kind of tedious to do it all on the home screen when there's a faster way. So get out your graphing calculator. I'm going to take you to the lists, and we're going to show you, take a look at how the lists would handle this. Okay, so hit the stat key and then the edit here. And we're going to go enter in numbers into our lists. I've got a lot of numbers in my lists. But really all you need to do is to clear list 1 and clear list 2. Now to clear a list, you move the arrow keys so that the list name is highlighted, and then you hit clear and then enter, and it wipes out the entire list. You can hit the delete key, but that just deletes one entry at a time, and if you have long lists, then there's going to be a problem. Okay, in L1, we're going to enter the populations. All right, so there it is. Just put those 5 numbers in list 1. Now I want to go back to a calculation that we've done already. And over and over and over again, you're going to be dividing these populations by a number. The number the first time was 50. We divided by the common divisor. Here, we're going to divide by 49.3. Here, we're going to divide by 50.65 and so on. But the last 3 methods are all very similar. All right, so move the cursor from this position, because if you're in here, then it's going to expect a number. So you want to move your arrow key up to put the L2 highlighted like that. If you highlight the list name, then you can enter in a formula. And what I typed on my home screen was all those state numbers divided by 50, divided by 50, divided by 50, divided by 50, right? And so what I'm going to do is enter a formula here. Highlighting L2, down in the input row, I'm going to hit L1 divided by 50. Now when I do that, it's going to divide every one of those numbers in L1 by 50 and put the answers right in here. So it's just 1 divided by 50 instead of having to do it over and over again. You can see how tedious that would be, particularly if you had 25 states and you had 25 rows of your table. You'd be dividing by 50 over and over again. Okay, the variable L1 is right above the number 1. So if you want to get L1, since it's in blue there, you have to hit the blue key first, the second key. Second, and then the number 1 would give you L1. All right, I've got my formula down here. Look what happens when I hit enter. it fills in all of these, and those numbers are exactly those that you see here. All right, you're going to do it again, but you're going to do it the next time. You're going to take all of those populations and you're going to divide by 49.3. And then we're going to write them all down. So as before, highlight L2, and then down in the input row down here, second, and then the number 1, divided by, not 50 this time, but we're going to divide by 49.3. And then I'm going to write down all these numbers. So here you can see the 22.56. This one is 22.68, and I'm going to round them to 2 decimal places, 26.78, 30.73, and 100.10. Okay, now, once you divide by this new modified divisor, the next step would be to round down. So that means just truncate the decimal. So 22.56, if you rounded that mathematically, it would be 23, but we're not rounding mathematically, we're rounding down. That means we're just truncating off the decimal piece. So 22.56 becomes 22. I'm just going to get rid of all those decimals. 22, 22, 26, 30, and 100. And sure enough, when you add those 5 numbers together, you get 200. So you can bet that these folks that created this system way back when, you know, they lived in a particular state and they had incentive to allow their state to get more representation than other states. So look at the numbers. State A gets 22 no matter what method. State B gets 22 no matter what method. But here is where we see a deviation. With Hamilton's method, C would get an additional seat, but with Jefferson's method, they would not. And this is an interesting case here because you'll notice that not only did state E bump up by 1, but it bumped up from the lower quota by 2. If that ever happens, then we say that it violates the quota rule. So if the number of seats allocated is more than 1, is not the upper quota or the lower quota, if it's not one of these numbers, then it violates the quota rule. And if the number of seats allocated to any one state is not the upper quota or the lower quota, then we say that it violates the quota rule. Okay, let's go to Adams. And by the way, I'm just going to come back up here and so that you can see this here. So choose a modified, for Jefferson's method, choose a modified divisor that's less than the standard divisor. So a number that's less than 50 would be 49.3. By the way, the 49.3, we're giving you this number because we know it works. In many cases, you have to determine what that number is. That'll be our second example. Okay, find the modified divisor, we did, such that when you divide each state's population by D, then round down to the nearest whole number, all of the electoral votes are allocated. So that's basically what we did. And then apportion to each state the modified lower quota. All right, let's look at Adams' method. Now, Adams' method kind of works in the same way that the Jefferson's method does, except the modified divisor, the standard divisor is 50. The modified divisor that you choose is not lower than 50, lower than the standard divisor, it's actually higher. And so you want to choose a number that's larger than 50. And so in our example here, we chose 50.65. It doesn't have to be very much higher than 50. It's got to be close to 50, but close relatively speaking. And because we're dividing by a larger number, the fractions will be smaller. And since the fractions or the modified quotas will be smaller, we will round them up to make them a little bit larger. All right, we're going to get the calculator out again. And since the new divisor is 50.65, remember that you have to go up. Here's what happens if you don't. I'm going to leave my cursor right here, and I'm going to type in my formula, which is everything in L1 divided by the 50.65. So L1 divided by 50.65. Now the calculator is not going to allow this because what it wants in the list are numbers, and you're trying to feed it, I'm trying to feed it a formula. It's not going to like that at all, and when I hit enter, it tells me something about a data type. So I'm going to go there, clear that out, go where I should have gone to begin with, up to L2, and type in the same thing. All right, so all the numbers in L1, the state populations divided by this new divisor, the modified divisor. The modified divisor in Adam's method, that is a little bit larger than the standard divisor. Hit enter, and then write down these numbers. Here's a 21.95, and as you go down, you have 22.07 and 26.06 and 29.91 and 97.43. Now, if you add all those numbers together, you'll see that we're significantly, not significantly, but we're lower than the 200. So what we're going to do now is we're going to round all of those numbers up to make them whole numbers. So even if you have of course, this number here, 22, would round from 21.95 mathematically, but this one would not. If we rounded this mathematically, it would be 22. But when we round up, if you have any fraction here at all, it's going to bump up the number of seats. So even 26.06, that one gets bumped up to 27. So you basically take the integer part and add 1 to it. Add 1, add 1, and add 1. And we chose a number, hopefully, that when you add these 5 numbers, you will get 200. Now, depending upon the method, state E could get 99 electoral college votes or seats, could get 100, or could get 98. So all 3 of these methods led to different number of seats. Didn't matter for state D, 30, 30, 30. Didn't matter for state A, 22, 22, 22. But it did change for the rest of these states. And this whole fight comes from how are we going to allocate those last 2 votes? All right, one last method, and it's similar. It's probably the hardest method because you either choose a standard or modified divisor that's less than 50, less than the standard divisor, or higher, and a lot of times you don't know which way to go. The other difference is that instead of rounding up or rounding down, round up, we're going to round mathematically. That's what round 4 or 5 means. If the number to the right of the decimal is 4 or less, we're going to round down. If the decimal to the right of the decimal, if the number to the right of the decimal point is 5 or more, we're going to round up. So we're going to round mathematically. That's what this means. All right. Now, once again, they gave us the 49.8 is going to be the modified divisor. So we're going to come up here and we're going to take L2 and give it the formula L1 49.8. And I'm going to write these down. 22.33 and 22.45 and 26.51 and 30.42 and finally 99.10. And the last step is a little different because now we're going to round mathematically. So the first number to the right of the decimal point is 3 here, so we round down. Here it's a 4, so we also round down. Here the decimal to the right of the number to the right of the decimal is 5, so we round up. So 26.5 is going to round up to 27. 4, so we round down. 30. 1, so we round down. 99. And if everything is done correctly, those should add up to 200. So that's it. It's a long example because usually in every problem, they want you to go through all 4 methods. But this is it. I mean, if you look at the arithmetic, we divided. We divided by 50 and rounded. Divided and rounded. Rounded up, rounded down. So conceptually know what you're doing. And that is, it's like taking proportionally. There are 10,000 in the population, and each one of these, if you take 1112 and divide by 10,000, you're going to get the decimal 0.1112, or about 11%. So since state A makes up about 11% of the whole population, then maybe they should get 11% of all of the seats. So if we take 0.1112 and multiply by 200, guess what number we're going to get? So they should get about 22.24 votes. So this is another way to think of how you calculate the standard quota, 22.24. 22.24. It's just proportionally. It's the fair way. You should be allocated votes based on the proportion of the population that's in your state. Okay, here's another example. I wanted to give you another context, and I wanted you to experience what it's like to have to select that modified divisor. So the first one we started with was one that the modified divisors were given to you. In this one, they're not. Okay, let's take a look. The context is different as well, because instead of being in a, in a country or that allocates votes to states or seats to states, this one is different. You have 250 nurses, and you have several shifts, and you want to make sure that you allocate the nurses to the shifts when there's the most patients. Like if there's 250 nurses and you have 5 regions, and why not just, here we have 4 regions, so why not just take 250 and divide by 4, get something along the lines of 62.5 or 63, and just give each one of those shifts 63 nurses. Well, the problem with that is that there are some shifts, like shift B, where they see more patients. So it would be nice to have the same nurse-patient ratio throughout the day. So we're going to assign more nurses in situations where we have more patients, and we'll assign fewer nurses on shifts when we have fewer patients. So it's a different context, but it's the same idea, allocating seats versus allocating nurses to shifts. Okay, let's see how it works. Step number 1, and so we have to take the total population, in this case, the total number of patients, and we have a nice little number like 2,000. Nice round number. So there are 2,000 patients on average, right? There are times when there are more patients in one shift than normal, than average. But on average, and this is what they collected their data, and this is what they know. So we take the total, in this case, patients, and we divide by the number of nurses. So instead of the number of seats, the number of nurses. What are we assigning? In the previous example, we're assigning seats to states. What are we assigning here? Nurses to shifts. And I believe that's 8. So that's the standard divisor. All right, so let's fill out. It's quick, it's almost automatic to complete the first 3 columns. So as we go from the patients to the standard quota, we're going to be dividing by 8. So when you add the numbers in the first column, you get 2,000. When you add the numbers in the second column, you get 250. All right, I'm going to do this on the calculator again, just so, because this is how I want you to do it. It's going to make your life much easier. All right, so I'm going to go change the numbers in these lists, and I just have 4 of them now. 453, 650, 547, and 350. The numbers in L1 throughout the entire problem will not change, but when you go to a new problem, you have to change them. All right, L1 divided by 8. Make sure again that you're up here highlighting L2, and then enter in those standard quotas. 56.625, 81.25, maybe I'll round these to 3 decimal places. 68.375, and 43.75. Oh, okay, complete the lower quota column and the upper column, upper quota column in the lower. Yeah, so put numbers in here. Remember, the lower quota and the upper quota will differ by 1. You're taking 2 numbers that kind of have the standard quota in the middle. Another way to think about it, truncate these numbers, put the truncated number here, and add 1 to the lower quota to get the upper quota. Okay, so I just really ignore what comes after the point. So 56, 81, 68, 43. 56, 81. No rounding going on here, but these do have to be whole numbers. And then we add 1 in each case, and we hope that whatever method we use, that the number of nurses that are allocated to these different shifts will either be the lower quota or will be the upper quota. We don't want it to deviate much from that. All right, let's see how many votes in Hamilton's method that we must assign to the shifts. So here we go, 56 plus 81 plus 68 plus 43 is 248. And since each one of these numbers is one more, you would actually add 4. And when you add those 4 numbers, you're going to get 252. Now we want to, we don't want to fire anyone. And so we're going to need to assign those last 2 nurses. If we use the lower quota, we've assigned 248 nurses, but we need to assign 2 more. So Hamilton's method is the method we use where we, by inspection, look at the decimal pieces. Go find the largest decimal piece. That shift is going to get 1 additional nurse. And then go find the next highest decimal piece. And then that shift is going to get 1 additional nurse. And when you add 1, you always add 1 to the lower quota. So the highest decimal is 0.75. So we're going to add 1 to the lower quota. After 0.75, the next largest decimal is 0.625. So we're going to add 1 to the lower quota to get 57. Another way to say that is we're going to use the upper quota. But these other 2 states, they are not changed, and so we're going to use the lower quota in every case except to those shifts that get upped by 1. And you should find that because we just added 2 more nurses to the 48, that we now have 250. All right, let's do Jefferson's method. Notice we have to come up with a modified divisor D. And you're usually not going to get it on the first try. For Jefferson's method, we want to choose a modified divisor that is less than the standard divisor. Now, the standard divisor in this case is not 50 anymore. That was in the previous problem. The standard divisor in this case is 8. So we want to go lower than 8 and then round down. In Adam's method, we want to choose a D that's larger than 8. But as you work with these, you'll get more experience. But larger than 8 does not mean 14. It means like 8.1 or something like that. And with this method, we're going to round up. In Webster's method, we're going to round mathematically. Did anybody try one? Guess what? This is what you have to do. You have to try one. 7's probably too low. Let's just do 7, just to show you that it's probably too small. And the reason why you want to put this into the calculator is because you're going to be trying different modified divisors over and over and over again. So let's see if we take L1 and divide by 7, and then we round down. So if we took 64, 92, 78, and 50, maybe I'll just add them down here. 64 plus 92 plus 78 plus 50, we would get 284. We only have 250 nurses. So if we went down as far as 7 from 8, we're going to create 34 additional nurses. We don't have that many. So no, you want to keep it really, really close to 8. So let's try 7.95. That's lower than 8, but not by much. So I'm going to come up here, and instead of dividing by 7, I'm going to divide by 7.95. You probably want to keep a scrap piece of paper handy and just keep track so that you can narrow down onto the the appropriate divisor. So when we did 7, I forgot what we had already. I think it worked out to 284. So now we're doing 7.95, and we're going to round those numbers down. 56, 81, 68, and 44. And those numbers add up to, guess what? 249. So we came close, but we didn't hit 250. So the divisor 7.95 didn't work for us. So we have to choose something else. Well, for just this first one, I want to do both of these. I want to do 7.94 and 7.96 because they're very close. And, you know, I want you to see if you choose a smaller divisor, what's going to happen to this number. If you choose a larger divisor than your last guess, what's going to happen to this number? So let's do them both. The first one is L1 divided by 7.94. And we're going to round those numbers down. So 57, 81, 68, and 44. And that looks like it's going to do it. On the other hand, if we happen to do 7.96 and round down, we're going to get 56, 81, 68, and 43. We're actually going to go in the other direction and get 248. Now, there's probably a whole list of possible modified divisors that will work. For example, you know that 7.94 will work. So maybe 7.941 will also work, or 7.939 will work. So there's probably a whole variety of ones. But what we do know is that 7.94 does work. So that's the number we're going to put here. So here's what you can deduce from this one example. If you do this method and you get a number smaller than the number of nurses you need to assign or seats you need to allocate, then if you want to bump this number up, you actually have to choose a smaller modified divisor. So go down. Okay, now what you want in here is these numbers here. So we chose, 7.94, and we got 57, 81, 68, and 44, and that adds up to 250. I am going to write the decimal versions just so you can see them. Again, please note that we're not rounding these mathematically, we're truncating, we're rounding down. Rounding down is the same thing as truncating the decimal. All right, for the next method, Adam's method, here's how you might want to deduce what an appropriate modified divisor might be. We do know that we have to select a number larger than 8. Here we had to select a number that was lower than 8. And what did we go down by? We went down by 0.06. So 8 minus 0.06 would give you the 7.94. So maybe what would work here is if we went up by 0.06. So why don't we try 8.06? That'll be our first try. We know we have to choose something larger. The formula is always the same, L1 divided by some number. The number we're going to choose here is 8.06. And there are the numbers. Now for this one, we're going to round everything up. So I'm going to bring my worksheet in here again. All right, so divide by the 8.06. Get these things here. These are called modified quotas. We're going to round each one of them up, not mathematically, basically truncate and add 1. And when we add these together, I think it works, right? 8 and 8, 16, yep, 250. Right on the nose. Since we did hit 250, we can keep with that modified divisor and enter those numbers in the Adams column. So again, I'm going to write both the decimal version and what we did with that number. round, in this case, round up. Now, when you get to Webster's method, you can choose the modified, you can choose the divisor, the standard divisor. You could use 50 here if it works. You could choose one of these other modified divisors that we've worked. The point is that we've already tried several numbers, and we know what the modified quotas would be if we choose those modified divisors. So what we can do is just round. We have 3 columns of rounded numbers. This one here is if D is equal to 8. This one here is if D is equal to 7.94. And this one here is if D is equal to 8.06. What we first should do is just to see if any one of those columns would work. So Webster's. If we have D equals 8, if we have D equals 7.94, or if we have D equals 8.06, we can write down the rounded numbers of these standard quotas. So for example, if we use D equals 8, this is 56.625. And if we round it mathematically, since that number right there is 5 or higher, we round up. 81.250 does not get rounded up. It's rounded down because 2 is less than the 5. 68.375 rounds down to 68. And 43.750 rounds up to 44. And when you add those numbers together, you get 250. So at this point, you're done because you match 250 perfectly. So what we're going to use is the modified divisor. We're going to round mathematically, and these are the allocations we're going to use. I don't even need to go further with these other ones because we found something that would work. So over here, we're going to let D equals 8. Instead of using a modified divisor, we're going to use the standard divisor because it works. And then we're going to enter in the same numbers, 56.625, 81.250, 68.375, 43.750, and then round them as accordingly as you must mathematically, and you'll see that all of those add up to 250. So you can see there's not a whole lot of difference in these columns. If you look at the numbers, they may be off by just one vote. But it seems like for Shift A, it looks like Shift A is going to get 57. Just about every method that we used came up with 57. Shift B looks like no matter what method we choose, Shift B is going to get 81 nurses. And it looks like Shift C is going to get 68 in every single method we chose. And 44 for Shift D. So this is one of those situations where it doesn't matter what method you choose, you're going to allocate the same number of nurses to the shifts. And there they are. It makes sense that Shift B gets more nurses than the others because they have more patients. But that's it. It's a long problem. You know, most of your homework problems will be a part of this. Sometimes they'll just ask you to do Hamilton's method. Sometimes they'll ask for a modified divisor. Sometimes they'll ask you to do all methods. But the 2 examples that we've done, the first one, the modified divisors were given to you. And in the second one, we thought about, well, what would the modified divisors look like? And we came up with those on our own.